people, welcome back. In this video we're going to do another example of hypothesis testing. I uploaded this question along with the textbook publisher's solution to it in this Google Classroom post, so you could find that PDF file if you want to do this problem on your own. We're going to go ahead and get started. In the 1980s, it was generally believed that congenital abnormalities affected about 5% of the nation's children. Some people believe that the increase in the number of chemicals in the environment has led to an increase in the incidence of abnormalities. A recent study examined 384 children and found that 46 of them showed signs of an abnormality. Is this strong evidence that the risk has increased? So, just like the last hypothesis testing problem we did, we're really asking ourselves how rare it is to obtain such a sample proportion. And it really has to do with sample size. The sample size is what allows us to determine how many standard deviations away from the mean that sample proportion is. All right, let's do each one of these 6 individual questions. I'm going to start out just by writing my hypotheses. So our null hypothesis is always the boring situation that nothing has changed. I'm going to write that by using the book's notation. H sub 0 is our null hypothesis, and that is that the proportion of children affected by congenital abnormalities is equal to 5%. Now for our alternative hypothesis, there's a little subtle clue given in that last sentence. Is there strong evidence that the risk has increased? Because it uses the word increased, I'm going to set my alternative as greater than 0.05. If it said, is there strong evidence that the risk has changed? I would have used a two-tailed hypothesis test because we would be interested in the possibility of it changing from 5% in either direction. But since it doesn't say change and it says the word increased, I'm going to use this one-tailed hypothesis test with the greater than symbol. If it would have said decreased, I would have used a less than symbol. Alrighty, so let's keep going. Part 2, or Part B, check the necessary assumptions. Just like when we did the binomial distribution model and the sampling distribution model for sample proportions and sample means, it has to obey all these conditions. The independence assumption, can we assume that these children in the study were randomly sampled and they're independent from one another? Yes. They were randomly sampled for sure. They had to use some type of simple random sampling. The 10% condition. Did we oversample the population? We're talking about the nation's children, so no, 384 children is not more than 10% of the nation's children. So we didn't oversample. We didn't sample more than 10%. And the success failure condition. In a sample of 384 children, would we expect under normal conditions to see at least 10 that have some congenital abnormalities? Is this greater than or equal to 10? Yeah, it's way higher than 10. 384 times 0.05. 19.2. So this is 19.2, which is higher than 10. And we'd expect to see at least 10 that do not have any congenital abnormalities. Yep, so we satisfied the success failure condition. All right, so all of our necessary assumptions are satisfied. We can start performing the mechanics of the test and finding the p-value. So what we mean by perform the mechanics of the test is we basically construct a normal model based on the null hypothesis. The null hypothesis was that only 5% of the nation's children were affected, and that's what we're going to set as our mean. That's going to go right in the center here. So our mean is 5%. And the standard deviation, we're going to use this formula, and the sample size here, 384, that goes in the denominator. And this is equal to 0.0111. Now what I usually do to label my normal model as I use this little trick in my calculator. I do 0.0111 x, and that counts x number of standard deviations away from the mean. And I just write the mean in there. Then I just go into my table, and I can count 3 standard deviations below the mean and 3 standard deviations above, and I just write in all those numbers. All right. Now, we have a sample proportion of 46 out of 384 children, and that's 11.98% or 0.1198. Where does that land on this normal model we drew? Well, it lands pretty far to the right. It's about 6 standard deviations above the mean, a little bit more than 6 standard deviations above the mean. So how rare is this to occur? It almost can't happen. Almost, 99.7% of all of the possibilities are contained within 3 standard deviations of the mean. And if we're all the way out here, what's the chances of obtaining a sample proportion that far or even further to the right? Well, to do that, we're going to use the normal CDF. I'm going to go on my calculator here. Second vars normal cumulative distribution function. I'm going to set my lower limit at 0.99 or 0.1198. I'm going to set my upper limit at infinity, and my mean at the mean of this probability model, 5%, and the standard deviation was 0.0111. All right, let's see what the probability of obtaining a sample proportion that far from the mean or further is. Well, 1.6118 E negative 10. What that E negative 10 means is that we have to move the decimal point 10 times to the left. So this is actually 0.0000000001612 if I round it there. So what is the probability of this occurring? Almost impossible. That is so close to zero that we're saying that this is almost impossible to obtain such a sample proportion if this really does have a mean of 5% and a standard deviation of this. So this is almost proof that it is not 5%. So explain carefully what the p-value means in context. The p-value of 0.00000000016 means that there is essentially a 0% chance of obtaining a sample proportion of 11.98% or higher under this probability model. Therefore, the true rate of congenital abnormalities must be higher than the 5% used in the probability model. What is your conclusion? In the recent study, 46 out of 384 children, or 11.98%, showed signs of abnormality. Our p-value indicates that there is almost zero possibility of getting such a high sample proportion if the true proportion of congenital abnormalities is truly 5%. This is strong evidence that the risk of congenital abnormalities has increased from 5%. Finally, do environmental chemicals cause congenital abnormalities? Well, there is strong evidence that the risk has increased from 5%. But there is nothing in this study that separated the subjects by exposure to chemicals and non-exposure to chemicals. And that's what we would really need to do in order to assert such a claim. We'd have to have a control group. So there is very strong evidence that the risk of congenital abnormalities has increased from 5%. While it is possible that an increase in chemicals in the environment has caused this increase, there is no way to prove this from this study. We would need to conduct further research to support such a claim. All right, problem is over. You can check the book solution to get a little bit more insight into this question. I see that 12 of you submitted your work this week. I was happy to see that, and I hope more of you do. Hopefully this video helps you get there. I look forward to seeing you later in our video meeting at 1:30. Thank you for watching.